Hello, everyone, and welcome back to Climate EDU. I am your host, Kayla Hathaway, and today I'm joined by John Doherty. He's a PhD candidate at the Environmental Geochemistry and Oceanography Research Group at the University of Hong Kong. His research utilizes various geochemical tools to explore phenomena related to climate, ocean circulation, marine nutrient dynamics, and environmental change on different timescales. In this episode, he's going to be talking about his ongoing research centering around physical drivers of ocean circulation in the polar and subpolar North Atlantic, approximately 420,000 to 380,000 years ago, characterization of these changes, and the impact of future emissions on nutrient circulation throughout the polar and subpolar North Atlantic. John, thank you so much for joining me today. How are you doing?
It's great to be here, Kayla. Thanks for having me. I'm doing great.
All right, so let's go ahead and jump right on in to this research. So since it's ongoing, want to go ahead and tell us like where you're currently at with it and the future steps moving forward.
Yeah, sure. So I'm currently a final year PhD candidate. So I'm trying to wrap up my projects, get things submitted, and hopefully published in the near future. So yeah, most of my research has been focused around, as you mentioned, studying ocean circulation, mostly in the past, and its implications for nutrient supply to the high latitude northern Atlantic region. So I have various timescales that I'm interested in, as you mentioned, sort of these past interglacial periods on the order of hundreds of thousands of years ago, but also more recently, over the last several hundred years ago, trying to characterize how recent changes in ocean circulation, driven by the larger climate changes we've seen today, are affecting nutrient supply to these regions. And then also finally trying to predict how these changes may manifest in the futures based on human emissions decisions and the subsequent global warming that we'd expect from them.
I can only imagine what it must have been like to offer this proposal up and be like, this is what I would like to research.
Yeah, no, I have a very supportive group here in Hong Kong. So in general, my supervisor has been very great at offering me advice and feedback on different ideas that I've had, and he's really helped me, I think, grow independently as a scientist and develop my own ideas. So it's definitely been a critical element. I think anyone doing an advanced degree, a master's or a PhD, really having a good advisor that's going to be supportive of you is an important part of that.
Yeah, I completely agree. Like making sure it's not about like just interviewing the programs, but also like interviewing your like advisors to make sure that you vibe really well with them for good
Yeah,
research.
yeah, exactly.
So, what inspired you to want to go and look at the past and just see what's going on with ocean currents for and these kind
Yeah,
of timescales?
so I actually started off in a marine biology lab. In my master's degree, I worked with Keo Kim, who's a marine biologist at American University, and he's actually a coral biologist. So I wasn't always interested in the high latitudes either, but I was interested in this group of organisms called foraminifera or forams. And these are essentially either little plankton or microscopic organisms that live at the bottom of the ocean. And they secrete these calcium carbonate shells, which get preserved in the geological and the sediment record. And so I was using them during my master's to look at environmental pollution. So looking at certain species that could be indicative of water quality. But it turns out that these little forams are actually the backbone of an entire field called paleoceanography, which is what I do more of today, is looking at deeper time oceanographic phenomena like ocean circulation. And so I had a background in identifying and working with these forams. And that was a large part of the project that I undertook for my PhD. So it kind of worked out. I wasn't actually extremely aware about the issues that I was studying that I ended up studying for my PhD back when I was a master's student. It was actually kind of a brand new project to me to work on ocean circulation, coming from more of a biology perspective. But that definitely worked out. I think I ended up learning a whole lot, and I really enjoyed it so far. And I definitely want to pursue this avenue of research further in the future. So I'm glad my journey took me where it did.
Hmm. And so with the first part of your research being the like the physical drivers of ocean circulation, and noted that it's an anonymously an anomaly of warm interglacial period that you that's called Marine Isotope Stage 11.
Yeah.
Um, and so is tell us a little bit about like what made this kind of like just strange and interesting to want to go and like dive into that specific time period of 420,000 to 380,000 years
Yeah.
ago.
Yeah, sure. So there's a lot of science to unpack in that sentence, actually, and I apologize for
Oh,
describing
no.
everything in jargon.
Go
But
for it. Go
I
for it.
suppose it's best to start with the definition of the Atlantic meridional overturning circulation, or what we call the AMOC, which is the system of currents that largely transports heat, nutrients, carbon from the lower latitudes in the Atlantic to the high latitudes. And this system of currents is critically important for global climate. For example, it's the reason why you have a milder climate over places like the UK, even though they're at similar latitudes of places like Canada, because the meridional overturning circulation works such that heat is transported in that direction. So there's a lot of interest in the climate science community for characterizing how the AMOC may have changed in the past, because it's changing right now. So there are now several lines of evidence to suggest that the AMOC is at an anomalously weak state over the last 150 years, coincident with the Industrial Revolution, which has been tied, in my opinion, very strongly to anthropogenic global warming. And so there's this ongoing uncertainty in the climate science community of how the AMOC will change in the future. And that obviously will have feedback implications for global climatic processes. So I would say that the past, my interest in the past is actually motivated by understanding these general mechanisms at play for understanding how the AMOC will change in the future. And we look at this particular interval, marine isotope stage 11, around 400,000 years ago, because this was a period in Earth's history that has been argued to be somewhat similar to the present day. So we had similar greenhouse gas concentrations, similar pre-industrial greenhouse gas concentrations in the high 300 ppm or the mid 300 ppm. And we also had similar orbital geometry. So the Earth was in a similar position relative to the sun. And
Oh,
so these
interesting.
are, yeah, so these are all these factors that essentially drive climate, right? So we think that this would be sort of an analog to the present and the future climate system. Now, this is there's the large caveat, because the Earth hasn't really experienced anything like what we've done to it recently. This is the largest rate of greenhouse gas emissions that the Earth system has probably ever experienced. And there's really no good paleo analog for the present and future state of the climate. But nevertheless, we look at these past warm periods to understand sort of maybe the general mechanisms that are at play and driving the ocean circulation.
That's so I had no idea that so like when you're like I was gonna say like oh wait astrology like wait no astronomy like we're not don't want to get those two mixed up here like so in your research also it sounds like there might be just a little bit of aspects from astronomy being taken into like guys you mentioned like the Earth's tilt and or
Yeah.
like not the tilt by like placement around the sun in order to my brain's going 100 miles an hour
Yeah.
because, as I mentioned before, this call I was in aerospace, and I'm just
Yeah,
here like, oh my
yeah.
god, this is so
Oh,
fascinating.
it's a good background. There are actually a lot of climate people. I saw about this recently. There are a lot of climate scientists that got their undergraduate degrees in astronomy, and the reasoning is or the hypothesis that was put forward was because in astronomy you study atmospheres on other planets, you study
Yeah.
things like orbital configuration. So there's a natural overlap between studying climate and astrophysics and astrochemistry and those kinds of things.
Mhm. Yeah, so that's just so interesting to me to see that connection and to hear it like be like, oh yeah, this is a, like because of this, and now today it's like ah that's my space nerd is freaking out now. So like but oceans. So like and so with the circulation and the second part so like earlier on you had mentioned like nutrients in the North Atlantic and so I is there like the second part of like your research mentioning of the characterizing changes in the circulation of nutrients
Mhm.
to the North Atlantic and the slowdown of circulation in the region. So my question here is, with it being a cooler time, is what it sounds like right now. You said, or we're heading into a warmer time with the
So, in terms of the non-anthropogenic part of it, we
mhm,
should be cooling down right now.
mhm,
We're getting warmer because of human activities, right? So, human greenhouse gas emissions are responsible for the warming that we've been seeing.
mhm.
But otherwise, without humans, we should be cooling back down. So, we should be heading back in the direction of what we would call a glacial interval, as opposed to an interglacial interval.
Okay, and so we're heading into that warmer time. And how does this affect the circulation of the nutrients, and like why does this matter for the North Atlantic? Like, does it affect ecology, like weather systems? Like, what's going on with that?
Yeah, yeah,
Mhm.
exactly. Actually, so one of the reasons that I really like the field of oceanography is just seeing how everything is kind of interconnected with each other. So nutrients are kind of like a currency for phytoplankton, and they're important because they're how organisms transfer energy back and forth between each other. And the AMOC, the system of currents that we were just discussing, transports these important nutrients to the higher latitudes. So it largely sustains, it's responsible for sustaining phytoplankton there. And phytoplankton are important for a variety of reasons. If you like oxygen, for example, they produce roughly half of the oxygen on Earth.
It's kind of
Uh,
important.
yeah, yeah, and they're also huge carbon sinks. So when we talk about carbon sequestration, there's really nothing else like phytoplankton to suck carbon out of the atmosphere. They also affect circulation patterns. I saw this really interesting study the other day showing how the distribution of phytoplankton can alter the biooptical properties of the ocean and impact things like sea ice and ocean circulation itself. Just the phytoplankton do this, and so there's really this interesting sort of physical, biological, chemical coupling that we always see in oceanography, which is always just remarkably fascinating to me as an oceanographer. But to come back to your question about the importance of North Atlantic nutrients and North Atlantic phytoplankton, these communities are actually super important, not only from a carbon sequestration and an oxygen perspective, but they're also important for supporting local fisheries, right? So things like cod industries and fisheries are dependent on phytoplankton as supporting the base of the marine food web. So without phytoplankton, without nutrients, we have less phytoplankton, and with less phytoplankton, we have less fish, which people like to enjoy and make their living off of fishing. So there are various dimensions of importance to these communities, and understanding how they're going to change, I think, is going to be a key environmental problem moving forward in this region.
Hmm. I mean, it's just kind of important to have fish in the ocean, like just one of those
Yeah,
things.
I did start off as a biologist, so I agree.
um, and that's so well that the fact that with the our chat currently is like, wait, roughly half the oxygen. That's so much. Like,
Yeah, yeah,
mhm.
yeah. Most people associate it with plants, right? So, a lot of my colleagues were a bit bitter when, not bitter, but obviously the Amazon rainforest is a very important element of the Earth system. It's very important environmentally and for social reasons and for conservation reasons. But a lot of my colleagues in oceanography felt like algae were not getting their fair shake at things, right? Because
Mm.
people were always concerned, well, the rainforests are the most important for oxygen, right? It's not necessarily true. The ocean is critical for supporting life on Earth, and also for supporting carbon sequestration. So if you like the air you breathe, thank phytoplankton.
Yeah, it's almost like I feel like there just isn't enough conversation around like the importance of the oceans. I mean, we have like just, oh, like don't put plastic in it, basically. But the conversation around like ocean acidification and how it affects, say, like kelp forests and that kind of thing, I didn't
Mm.
really hear much about it until I got into like college level um coursework, which I found interesting. But with like forests and like trees, we like basic understanding, like, from young ages, like trees are good. we need them.
Yeah. I mean, it's fair because we live on land, right? We don't live on the water, and the ocean is so large, and in most people's opinions, it's quite empty, right? And these phytoplankton are mostly microscopic organisms, so it's understandable that people could associate environmental protection and conservation with trees that you can see on land where you live. But really, it's sort of these unsung heroes of the climate system are the phytoplankton and the algae in the ocean.
Hashtag save the algae.
Yes.
And so like with the methods and methodology for this kind of research, I'm curious like what kind of tools and techniques do you use to go and really like dig into the analysis, especially on like the kind of time scales that you're working with. Are there like are you doing core sampling or just like water sampling? Like what does
Yeah.
like a day in the lab or the field kind of
Yeah,
look like?
yeah. So it depends on the time interval. So for the deeper time stuff, the past interglacials on the order of hundreds of thousands of years, I use microfossils like foraminifera or forams. And I look at their geochemistry of their shells, and their chemistry actually records things like the temperature, the salinity, the nutrient concentrations. All of these things can be detected in the chemistry of foram shells. So they're kind of like these ancient little floats. For example, today in modern oceanography, we have floats that detect these things that measure things like oxygen and ocean circulation and nutrient concentrations. These forams are essentially ancient floats that have been deployed over the past several million years and have been recording information about the ocean. And so we can measure the chemistry of those shells and derive information about the ancient ocean based on the foram shells. On more recent time scales, so over the last several hundred years ago, I use coralline algae, crustose coralline algae, which are long-lived calcium carbonate secreting algae that produce growth bands similar to trees. And so
Ooh.
you can go in and you can actually sample every year for the last 600 years and do your geochemical analyses and reconstruct sort of the similar phenomena about ocean circulation and nutrient concentrations and what have you about the historical ocean.
That is so fascinating. Like that it like so imagining like basic the image that popped in my head is like underwater tree basically like you know how you take like you know just a cross section of a tree and it's like okay here's the rings. I'm like wait okay so
Yeah,
doing this but with algae like what would
yeah.
a
So
cross section of this look like?
Yeah, so corals actually do the same thing. A lot of species of hard corals have growth bands, which you can conveniently sample and get a high resolution reconstruction of different oceanic parameters. Coralline algae have the advantage of living at high latitude. So lots of hard corals, they live in the tropics and subtropical regions. So you don't actually get any information about the higher latitudes. And crustose coralline algae are found throughout the global ocean. So I think it's an underutilized archive that we can get way more information from.
Well, I'm definitely excited for when that like manuscript. I think you know, mentioned that that one's in you to see like if there's any like images or figures in relation to like what this looks like. I'm really looking forward to being able to check that out. And so like for the part three of this like so like the impact of future climate emission scenarios on nutrient circulation throughout the polar and subpolar North Atlantic. Like what I guess this is sounds kind of like your conclusions that you're drawing from all this research that you've been doing for your PhD, and what are you, if you're able to say now, like do you think is your grand finale for this giant this big
Yeah, so
project?
this is actually my most recent project, and these are the results that I'm least confident in. I will preface it with this.
Okay.
But so I've been using some mathematical modeling to predict how different emission scenarios will impact nutrient circulation via their impact on ocean circulation. So several all climate models predict a weakening in the AMOC. And all climate models predict a weakening in the nutrient supply to the polar and subpolar region. So what I'm trying to do is go one step further and see how these changes occur on a regional basis. So for example, how do they occur in the subpolar region versus the polar region? under different climate emission scenarios. So the IPCC, or the Intergovernmental Panel on Climate Change, has a list of likely emission scenarios, which result in different changes, different levels of global warming, which impacts the ocean circulation in different ways. So I'm trying to use mathematical modeling to understand how those emission-specific changes to oceanic circulation will impact the supply of nutrients to these regions, and how the supply of nutrients will subsequently impact things like phytoplankton growth and carbon uptake. I will say, yeah, this is, again, this is a project that's really just begun. So I'm not super confident in sharing any results that I have just yet, but I'm hopeful that we can work out an interesting conclusion from it.
Well, once you do have the final conclusion for that, you're more than welcome to come back on and be like, all right, I have the answer now, guys.
Yeah.
Well, this has been wonderful, and like finding your finding you on Twitter and like digging through some of your research, I was really excited to be able to chat with you. And I would, if you are ever interested, I would love to definitely have you back on to talk about the 2018 publication that was talking about, I think it was the colder surface temperature for like the Nordic Sea.
Yeah. So this was about the marine isotope stage 11 interglacial that we were discussing in the beginning.
Yeah, like if you would ever be interested or have the time to do a deep dive on that kind of research, I would love to have you back on as well.
Okay.
And because then adds like all the fun additional context, like for your big projects.
Yeah, totally.
Yeah.
Well, thanks so much for having me, Kayla. This has been fun.
Yeah, so I'm going to go ahead and roll the credits and we'll head into just chatting. So we'll be right back.
Okay.
Now we can let our hair down.
Okay.
Yeah, so chat saying Reese is like, yes, I would love to hear John come back and give us an update. Let's see.
Great. Yeah. It's a busy time for me being a final year PhD student, but maybe in the future I can come back at some point.
Yeah, and I mean, how has it been? So being in a final year, well, I mean, you're also like in Hong Kong, and we were mentioning like before everything, like COVID's kind of not as gnarly there as it is here in the States. So I was gonna be like, oh, how has it been doing everything online? Then I'm like, wait.
Yeah. So that's one advantage, is that my lab actually never closed down for COVID. So I know lots of colleagues of mine in the U.S., they had to close their labs down for a certain period of time, and I could just do my research, and so that's definitely one advantage.
Mm-hmm. Yeah, like, so what's it like being in your final year of research? So, because with this kind of degree, is it one big dissertation, or it sounds like you're doing kind of like multiple publications as opposed to one giant thing?
Yeah, so it's similar. It's a mix between sort of the British and the U.S. system. I'm not sure if you're familiar with it, but it's mostly a research degree. So it's not so much about classes, but you're expected to do a variety of research projects that count as chapters to your PhD. So you usually have 3 or 4 chapters, which ideally are 3 or 4 things that can eventually be published. And you call that your thesis or your dissertation. So it's similar to the US and the British systems. But the US, you usually have the first 2 years, the first 1 or 2 years in the US, you usually are focused on coursework. And then you have 3 or 4 years to do your research. So here in Hong Kong and in the UK and in other European countries, you usually just do the research part. You don't do the coursework.
Interesting. So like a lot of the coursework is more so like in the master's programs or like undergrad?
Yeah, undergrad, and in master's degrees here also you don't do a lot of coursework, but I guess they expect you to have a strong background from your undergrad. I mean, I'm thankful that I did my master's in the US because I felt like I did have sufficient coursework background to start my own research. But I think it would have definitely been difficult to come straight out of undergrad to do a 4-year research PhD without additional coursework. So
Yeah, I'm always in awe by the people that are like, "Hey, I just got my bachelor's. Now I'm going for my doctorate." And I'm like, "Good luck."
Yeah. Yeah, in the US, I think that's more possible because you essentially do a coursework master's before you start your PhD. If you do your bachelor's, you finish your undergraduate coursework, and then you have 2 years of coursework, advanced coursework before you start your research. And I think that's a good way to do it. So that's sort of how my master's in the US was. It was sort of half coursework and half research, whereas my PhD is just 4 years of pretty much pure research.
Man, yeah, there was a couple master's programs I was looking at. There's this one in England that's like it's just all research and like no exams. Like you just go and they're like, here's this project. Your whole year is to just work on this and like find a
Yeah,
solution. And I'm here like, what?
yeah.
I don't have to go and just grind information. I get to just work on things if I choose
Yeah.
to do that. So that's been
They,
like,
they actually they make our undergrads do that here too, but they also are expected to take coursework. So the final year undergrads at Hong Kong U where I am are actually quite busy because they have their final year projects, which are essentially miniature theses, on top of finishing up their bachelor's coursework. So those students are always pretty busy.
yeah, I can only, oh man. I can only imagine what finals week must feel like. You're just there like
Yeah,
just start injecting the caffeine directly into
yeah,
your system.
yeah.
uh-huh. Um man, and let's see, I wanted there was one other question that I wasn't able to um I mean you kind of answered like the geochemical tools kind of answered like how you go and like take the coral, the algae and everything, but like what's like the actual like tools that you're using, like the hardware?
So it's mass spectrometry, which is a way of characterizing the mass of certain elements. So I mostly look at nitrogen, which records nutrient processes. And what I do is I look at the stable isotope ratios of nitrogen from my samples. So the essentially every element, not every element. So nitrogen has two stable isotopes. It has a heavy isotope N15 and a light isotope N14. And so characterizing the changes in the ratios of those two isotopes for biochemical reasons tracks things like how much nutrients are available in the ocean. I don't. It's hard for me. I'm sorry to explain this in a non-technical way.
Oh no, no, you're good. Like I have I made it up to OChem, and so I kind of understand like,
Okay.
oh, okay, but that was OChem was a lot.
Yeah.
Like
Yeah.
I didn't believe people when they were telling like, "Oh yeah, like it sucks." I'm like, "No, like I'm sure it'll be fine." Then I'm like, "Oh."
Yeah, yeah, that's usually the one that leads people out of the pre-med program, right? Where
Mhm.
I know a lot of people that are like, I'm going to be a doctor, and then they take organic chemistry, and like, no, I'm
It's
not.
like, actually, I'm just kidding.
um,
Oh man. Well, I do need to start wrapping us up here because we have another episode in about 30 minutes. So, but I
okay,
thank you so much for joining me. And I said anytime you'd like to come back on to just like casually talk or do kind of like a produced episode like this about research, you're more than welcome to. And I'll send an email to you within the next like day or two when it's ready to be downloaded. Um, and yeah, it's been a pleasure, and I hope you have a wonderful day.
thank
It's
you.
time
Yeah,
zones.
great. Have a good evening.
Yes. All right. Talk soon, John.
Okay, take
Bye.
care. Bye bye.
All right, lovelies. So we have another episode coming up with Lee in 30 minutes. Going to be talking researching school strike for climate in Australian youth attitudes. So it will be wonderful. Lee is an incredible partner, and I always love when she follows up my episodes. So hope if you have yet to go get water because water is important. Remember, we are just like houseplants. We need sunlight, water, and fresh air. And I look forward to seeing you all again tomorrow at 3 p.m. Pacific. I will have Andre on to discuss The Urban Heat Island Effects in and Air Pollution in Richmond, Virginia, with his recent I can't words. His recent publication. So it's wonderful, y'all, and I will see you again tomorrow.